Thank you very much for the invitation and for the introduction. So today I will talk about B-series. I work in numerical analysis and I like to use algebra for computing and finding efficient methods. So I will try to present to you these B-series that are completely new as an extension of the standard B-series and the aromatic B-series. This is joint work with Gilles Villemar in Geneva and Hans Muntekas in Bergen. And I will try to go slow on the numerical analysis part, so everything is fine. So let's play with some particles. So see, we will try to do some stochastic numerical analysis. We will try to study this SDE up there. It has some additive noise for simplicity, but also because it's the one that appears in in practical physical applications. F here is a gradient of the potential. And the first question that arises is this SD appears in practical applications, and I want to make a simulation to predict the solution of it at some time. And the question is, I'm a numerical analyst, what do I want to approximate? And there are many answers. It's not as in the deterministic setting where you can just approximate y of t. In this setting, you can say, I have access to the complete randomness of the system, and I want to approximate the solution x of t. So I have access to w, I want to approximate x of t. For these particles that satisfy this equation, it means approximating the motion of each and every particle. It is very costly, it is called a strong approximation, and it is useful in practice in some applications. For this kind of system that appear in molecular dynamics, actually, the dimension is very high, ideally 10 to the 24. So we cannot afford to do this. And if you work with particles, let's say you want to make a weather forecast, you do not actually care about the exact motion of every particle, but you care about some average of some quantity of the that depends on the solution. For instance, the temperature. The temperature, it's the expectation of the velocity squared of the particles. And for these particles, it means approximating the law of x of t. This is a weak approximation. We will begin with this. And there's another one. Let's watch the animation again. See, I put a lot of particles together. They do not interact. They just follow the same equation here with different initial conditions. And you may think that they can evolve only in the box, but they cannot. They actually evolve in R2, but they do not get out of the box, because the potential that I chose confines the particle inside. And actually, you can see that the system reaches some kind of equilibrium, and the particles gather here, 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 and here. And if we watch it for a long time, it's even more obvious. This is a third kind of approximation, and I will focus on this one for this talk. It is an even weaker convergence. It is a convergence for the invariant measure. We approximate the law of x of t, the temperature of the system, but at equilibrium. All right? Of course, the same can be done if the system satisfies some geometric properties. So here, it's a very simple one, where the particles actually satisfy an invariant that lets them evolve only on a circle, a manifold, and a simple one. You see that the particles, again, they gather at some places because I chose a potential that forces them to do this. And in this kind of context, you have an additional difficulty as a numerical analyst. You want the solution to stay on the circle, to satisfy the same kind of geometric properties. It actually had some additional difficulty. All right. So now, how do we understand this property? It's called ergodicity. It means that the average here of the temperature, the function of the solution, in long time is a deterministic quantity. It behaves like the same functional integrated against a certain invariant measure. And this is the Lebesgue measure in RD and the canonical measure induced by the Euclidean metric on the manifold. And you see that here is this rho infinity called the Gibbs density in physics, plotted for the example that I gave at the beginning. And you see that the particles indeed behave according to this density in long time. The same thing happens on a manifold like this torus or any manifold that is smooth enough. All right. So let's go back to some numerical analysis. In numerical analysis, we have many ways of evaluating the efficiency of an integrator. And one that we will talk about today is the order, is the accuracy. The order of the method, you make a Taylor expansion and you see to what order it's exact, and that's basically the order of your method. So for this particular problem, we name U what I call the temperature, the average of a functional. You can show that it satisfies the parabolic PDE, and for a weak approximation, that is the quantity that you want to approximate. For this parabolic PDE, you could think, well, just solve it. It's way easier than doing some stochastic, but you cannot because you work in high dimension. It's a very hard problem. So instead, we will use this generator and we'll make a Taylor expansion of U. So L in RD, it's given by this operator. It's phi prime f when I use, which means the sum of di phi fi plus a constant times the Laplacian. This is very important because we will try to represent such operators, and to do this, we need to be able to represent standard derivatives with standard B series and Laplacians that are completely new. On the manifold, it's even harder. You have standard derivative, Laplacian again, and some divergences, hence aromatic, V series, some scalar products, and then that's all. So we have to be able to represent all of this. And the talk is about introducing a formalism to be able to compute these order conditions. Okay, so let's do a Taylor expansion. We have du over dt is equal to L of U, so that means that U is exponential TL of phi. So it's phi plus HL phi plus H2 over 2L2 phi, etc. And we assume that the numerical scheme, I will introduce an example soon, satisfies the same kind of expansion. And so what we do is that we compare the terms. If L is equal to A0 is a differential operator, then we have order 1. If in addition L2 over 2 is equal to A1, we have order 2, etc. All right. So this is called the Talay-Tubaro expansion in numerical analysis. And if the operators are the same up to order P, we have weak order P. Again, this is not the error that we will talk about, but I need to introduce all of this. Now let's take an example. So to create a numerical scheme, I take a time step h, that is I replace dt by h, and I try to approximate my solution at discretization. So at time 0, h, 2h, 3h, etc. And I replace dx by xn plus 1 minus xn, dt by h, f of x by, so that it's not completely simple, convex combination of f of xn and f of xn plus 1. So if theta is equal to 0, it's the Euler scheme. And we replace dw by a Gaussian that has the same law at times t. Okay? Because we care only about the law of this process. We can prove that it actually satisfies this kind of expansion with these operators. We have A0 is equal to L, so it has order 1. It's not a crazy method. And A1 is given by this. Okay. And now we need a bit of algebra because this is the simplest term, the simplest non-trivial term, and it quickly gets tedious. So we will try to represent these differentials with trees. That is, we will represent these. So you see that we have a test function phi, the function f, that is from RD to RD, and some Gaussian standard laws, random variables. All right. Yeah, of course. Here? Yes, sorry, because it's a typo. It's x1. Yeah, I mean, it's x1 is the approximation of x of h. Okay, that's where it does come from. Exactly. I should have said that. All right, so let's do some trees now. We forget about the numerical analysis, we do some algebra. So the B series, as I will present them, You can compare them with the work of Butcher, introduced in the 60s, that were formalized in Innsbruck and Geneva by Hairer and Vanner. When I say Hairer, it's the father, not Martin Hairer. And then it was used everywhere, and especially in the field of geometric numerical integration. So basically, each node represents a function. The root of the tree will represent the function phi, the test function. All the other nodes, they represent the function f. So that's phi, and when I draw an edge between two nodes, I derive the bottom node in the direction of the top one. So that's phi prime f. Then here you see that I derive the bottom node 2 times in direction of f and f prime f, and you can define the differentials recursively. Consider an extension called aromatic forests that was introduced for creating volume-preserving integrators, and that actually is used at other places. So basically, just keep in mind that we represent a divergence with this graph. This is like you derive this node in the direction of itself. It's the sum of di fi. All right. And finally, last extension, almost, we use some crosses to represent the Gaussian laws. So forget about the constant. This is phi second, 2 edges, in direction of f prime xi, the random vector, xi here. And okay, nothing is new here. This similar formalism have been done before, but it was used mostly to study strong and a bit weak error with a lot of trees that are actually not needed. So we need an extension to represent this Laplacian that I was talking about. Hence the lionas, and the name exotic. We need to represent this Laplacian. We need this dashed edge. That means that we derive the node 2 times in the direction of the canonical basis, and we sum. The sum is very important because we want the trees to not depend on the dimension, because the dimension is very high again. This is dii phi, and that's the Laplacian. So you can make some very complicated differentials like this one, and the point is that this formalism is exactly what we need for this kind of numerical analysis. And we will see that it is a natural extension of aromatic B series. All right, let's use it now. So we have this expectation for approximating x of h, and we want to compute the expectation of this linear combination of differentials. So we replace everything by trees, and you see that the expectation applies only on crosses since they represent the random variables. So when you take, if you remember the talk of Frédéric, the lecture of Frédéric, we saw that taking the expectation of Gaussian random vectors is the same as making pairs of them and multiplying covariances of pairs of them. It's the same here, actually. When you take the expectation of like this tree, you just have to link the crosses by a liana, and that's how you compute the expectation. That's the first simplification. And for the second one, let's go back to this invariant measure error. The idea is that we had this condition that the operators should match in the Taylor expansion. And if they match up to order 2, we have order 2, up to order 3, we have order 3, etc. If you work for the invariant measure, you work in a quotient space where you allow the integration by parts. So if this is satisfied, that is, if the adjoint of aj applied to rho infinity is 0, that's the criterion that we have for order p for the invariant measures, for the approximation of the temperature only at equilibrium. You can prove that you can use this criterion in practice, and it's an even weaker error than the weak error. It's the one that is used in practice for simulations by engineers and physicists. And the point of considering it instead of the weak approximation is that you can create some surprising schemes. Like for us, if you want order p, you need all p evaluations of the function f. That's like a law, an axiom. And this is not the case for the invariant measure. For instance, this one has weak order 1, but order 2 for the invariant measure with only one evaluation of f. So you can create some very cheap methods very surprising with this error, and that's the goal of this talk and all this formalism. So to compute this integration by parts, you can actually use the trees. Before it was done by hand, it was very tedious and not always accurate because it's a lot of calculations. With the trees, it's very simple. We have a Python program that can do it for you. Basically, if you want to integrate a tree, the differential operator associated to a tree by part, you just unplug an edge, for instance, the Liana here. You plug it to all the other nodes, you get this one, or you plug it to a new node with a normal edge. And that's how you do integration by parts. This thing is something that a Python program or in any language, a program that can do. Yep. Capital F, it's a differential operator associated to a tree. Like, do I have some talk? Yes, I do. Here, good. For instance, for the tree we consider here, this is a differential operator applied to phi, and it's exactly equal to Laplacian of phi prime f. Okay. Laplacian for the Liana, then prime f. Well, I don't talk about it very much because it actually, if you fix the constant in time of the noise equal to square root of 2, you can get rid of it. But it's it comes from the expression of the Gibbs density. But we can get rid of it. It depends of your choice for the SDE. For our example, we can perform the integration by parts, and we find this integrator. So this operator has order 2, and this one has order 1. We integrated by part. We lost an order. And so you see that if theta is equal to 1/2, this is equal to 0. And so we have order 2 for the invariant measure. All right? So, okay, this is a nice formalism. Now I will do a bit of numerical analysis and play with it. So we introduced some Runge-Kutta methods. So this is basically an extension of what you saw before. We have substages that approximate the solution at a time between 0 and h, basically, for making it simple. And then you use these substages to perform a last approximation. And so you have some coefficients bi, aij, and di, which allow you some freedom. And you translate basically the order conditions with these coefficients, and you link them with their corresponding trees. So for instance, this is the condition for weak order 1, and we have 2 conditions for order 2 for the invariant measure instead of 3, 6 order conditions for order 2 for order 3 instead of 9, 6 instead of 9, and it grows exponentially. And you can simplify it even more if you add some assumptions. So if just a commentary for numericists, if you know a bit about the Runge-Kutta condition, you could think if I erase the noise, this term disappears, and this sum, this di, should be 0. So I get the condition sum of bi ci is equal to -1/2, which is not the condition for order 2 in the deterministic case. You could think this is wrong. This is not. I hope. It actually comes from the fact that you cannot get rid of the noise. This kind of approximation is specifically designed for stochastic differential equations. If you erase the noise, you cannot reach the equilibrium. There is no ergodicity. Thus, this does not apply. CI, it's a sum of aij on j. This is a convention. Sorry, I'm sorry. This is the kind of thing that I cannot think of because we use these notations all the time. Thank you for noticing. So of course, this can be extended on in several contexts, and especially on manifolds. I will not talk about it, but just instead of 2 order conditions, we would get 22. So this is why we need a formalism, because the calculations get tedious very quickly. All right, and just for the extension on the manifolds, I talked about the scalar product at the beginning of the talk. So here's the extension. Don't mind the colors, but basically we have two kind of nodes. One for the gradient of the constraint on the manifold, one for phi and f, and we introduce this new kind of edge that represent a scalar product. So you can represent the generator L on the manifold with trees. I will go quite fast on this. And well, you can perform the calculation, but the number of terms is horrible. But I just want to mention this extension, because if you take the trees with the lioness, with the aromas, with the scalar products, you have the right extension to aromatic B series. Why? Because it was shown for, I say this because it was shown for aromatic B series that they satisfy some geometric property that if you have a function, certain kind of map that is local and affine equivalent, that is invariant under an affine change of coordinate, you can prove that it actually has a Taylor expansion that can be written with aromatic B series. Or if you replace affine equivalent by isometric equivalent, you can prove the same with these, with a slight extension of it. This is left for another talk. So that's why I say that these are a natural extension of aromatic B series. All right, so let me finish with a numerical experiment. So on this torus, we let some particles evolve with a potential that confines the particle on top of the torus. We apply the Euler method, the simplest one. It has order 1, and the new method has order 2. And you see these things come from the Monte Carlo error because we have some noise. So typically you can add and combine some other methods to reduce this noise. Anyway, I just want to show you this. These are the two first pages of 7 pages of calculations with trees on the manifold. Why I am showing this? Because you usually don't show your horrible calculations. It's because I want to convince you that algebra and this kind of structures is a necessity for numerical analysis and for this kind of problems. Because this SDE is a simple one, and yet on a simple manifold, we need to compute all sorts of terms. We need a program to compute all these terms because it takes a while. It's already hard enough even for order 2. So that's why we need some algebra to help us. So as a conclusion, I just want to say that we introduced a formalism that is fit for computing all the conditions for numerical methods on manifolds or in RD for solving stochastic differential equations for a specific kind of error, which is the invariant measure error. It can also be applied for weak approximations. It's also a nice formalism in this setting. And we introduced one particular example of an order 2 method that works on the manifold, and that is the first one. For future works, we have 2 directions. One direction that is numerical, that I won't talk much here, but basically you can extend it with node gradient forces, and in particular cases, we have many questions. But for the algebra part, the algebraic structure of these B series is not known. It would be especially interesting to do some backward error analysis, which is something that we plan to do in order to find the operations that should be added on these structure of B series. And we have, there are plenty of questions because we have a lot of works on standard B series and aromatic B series. We could generalize them to exotic aromatic B series. And yeah, this last work that was just submitted that works in the vicinity of a manifold, because we have some methods that work on a manifold in RD and would like to make a bridge between them. But I think it's 25 minutes, so I will thank you for your attention and stop here. Questions?
I have a question. Did you consider also equation? Because you say, okay, generalization like with more crazy manifold, but like with multiplicative noise.
Yes.
But on like RD.
Yeah. So
You
I am considering it. The main problem is that we don't have this. I mean, we don't have access to the invariant measure, so it's not straightforward if this really helps with the other conditions. But we are investigating it. It's much harder, especially because you cannot just consider simple Runge-Kutta methods with Gaussian noise. You have to introduce some other kind of random variables. Uh, this is work in progress. But we can talk about it later. This is quite an interesting question. I mean, you can adapt the formalism, but I would say that the most important question is to find the right class of methods. And this is not clear for me. Yeah. Yeah. Yeah, actually, so we indeed approximate the solution at finite time that is large enough so that the convergence to infinity can be observed. In practice, you can prove that the error is made of three terms. The one that I studied, the numerical error. Then you have the error, the Monte Carlo error. Then the error of convergence to equilibrium. And you can prove that it has a form constant exponential minus lambda t, with lambda the biggest eigenvalue of the generator. And anyway, it's exponentially fast. But there are some numerical methods specifically designed for accelerating this convergence. Yes, especially on the manifold as well. You could imagine a manifold with like two balls and the bridge between them and or metastable potential, and the convergence would never been observed in practice. So, yeah, other questions. So actually the manifold case, in the manifold case, you already have an hypoelliptic operator, so we had to treat that. Especially, it's very interesting. This question is very interesting because this dynamic that we chose is not the most useful one. You usually study the underdent Planchon dynamics, and then by definition, you don't get a full Laplacian. So yeah, work to be done. It's ongoing work with Tony Lelièvre in Paris. Thanks. Yeah.
A very quick question. What do you mean with symbolic manipulation? Like rewriting systems, or what do you have in mind?
I mean, okay. I mean, I just mean that we use SymPy. But no, not yet. Yes, we have composition, actually, yes. We have composition and all these operations that I showed. We don't have substitution yet, but I mean, yeah, well, this program is just does the operations that I showed you. So, but I guess when we use these simplifications, some people try to do these symbolic calculations with functions directly, and it doesn't work in practice. It's quickly too hard. And this I don't know. We have to. Okay.